Video beginning. All right, welcome to this video on writing segment proofs. The first video, it's actually going to be done in two parts. We're going to go through the rules commonly used in segment proofs. And then in the second video, we'll actually practice writing some segment proofs. Keep in mind, we are going to be using our old algebra rules as well. Things will build and snowball a little bit as we go through it. So some things commonly used in segment proofs, and I will highlight the ones that are most often used as we go. The definition of a segment is that basically we know it's a part of a line with two endpoints, a subset of a line really. I'll be honest, I can't think of an example in which we would use that in a proof, but I still am covering it because it goes with segments. Next, congruent segments. Well, congruent segments are two segments with the same length. We will use this a lot, so I'm going to highlight this one a whole bunch. So we will use it if we have two segments that are given as congruent. Like AB is congruent to CD, we will use congruent segments definition to say that that means they are equal in measure. So we may have AB congruent to CD, and then in the next step, we say the length of AB is equal to the length of CD. I know that seems really weird because it seems like congruent and equality are the same thing, but they are not. For segments, they are. For angles, they are. But when we get to more complex figures like triangles and rectangles and stuff, it's possible for two rectangles to have the same area. So they have a measure that's equal, but yet those two rectangles are not congruent. So like, for example, maybe you have a 3x12 rectangle and a 4x9 rectangle. They have congruent area or equal areas, but they are not congruent rectangles because their sides are not all the same. So congruence and equality really are not the same thing when you get to more complex shapes. So we separate them for segments and angles as well to keep it consistent. Betweenness. Oh, by the way, with congruent segments, not only can we use it to go from being congruent to being equal, we can also use it going from being equal to being congruent. So you could conceivably use this twice in the same proof. All right, betweenness, we know what that is. A lot of times that'll be given in the given information. We won't really use it to justify something in the middle of the proof, but we know that like A dash B dash C means that B is between A and C, but not necessarily in the middle. So I purposely, if it doesn't say bisect or midpoint, I purposely don't put it in the middle because I don't want to trick my brain into thinking it's in the middle and then using that in my proof. So I purposely skew it to one side or the other. A lot of time that will be part of your given info. Okay. Segment bisector. Okay, usually that will either be in your given info or what you're asked to prove, given / prove. And it will be something like, if a line bisects a segment, prove something else is true. So, a bisector can be a line, a ray, a segment, a plane, even a point that divides a segment in half. And then a midpoint, of course, is a special kind of bisector where it's a point. We know what a midpoint is. So these kinds of things could be in the given and prove information. All of these are definitions. So if you use them in a proof over to the right, you'll write definition of these things. So you'll use these too. Okay. All right. Postulates. Line postulate. We will use that a lot, just not in this unit. We'll use it later. But basically, we're going to use that to justify that 2 points make a line. Okay, so a line is part of a segment, so I'm including it with our information on segment proofs. But the line postulate was one of our postulates to say 2 points make a line. And this is a good time for me to bring up the fact that if you can't remember, it's called the line postulate. You could just write in your proof for your reason 2 points make a line, and that's equivalent. You can write the name of the rule or what the rule says. Both of them are equivalent, mathematically accurate, and would get full credit. When we're going to use that later on, I think I'm going to switch colors here so that things don't get too mixed up with the other sections. 2 points determine a line. Later on, we'll be proving things about, say, parallelograms, okay? And we may prove that a parallelogram, for instance, has the opposite sides equal. One of the first things we're going to do is take this point here and this point here and connect them and say we're allowed to do that because 2 points make a line and a segment is part of a line. So we will use that a lot later on, not so much right now. So if I have this picture with A and B implies that the line or the segment AB exists. Segment addition postulate, I'm going to highlight that because we're going to use it a lot. Okay, so we know that if B is between A and C, then we can conclude that AB plus BC equals the length of AC for sure. Ruler postulate we will not use a lot. It's the same as distance on a number line that says basically, if you have a number line with 2 points A and B, that you can find the distance from A to B by doing absolute value of A minus B or absolute value of B minus A. I can't think of any examples right now. There might be one all year where we use that. So we're not going to focus on that one too much, but I'm including everything that has to do with segments that could possibly conceivably be in a proof. All right, midpoint theorem. Midpoint theorem is different than midpoint definition. Midpoint definition basically is a special kind of bisector where we can use it to conclude that, if M is a midpoint of AB, then that would mean that AM is congruent to MB. It creates two congruent segments. The midpoint theorem, which we will be proving actually later in these notes, says that if M is a midpoint of AB, then it doesn't conclude that the two parts are equal. It concludes that each part is half of the whole. Okay, so write down the other one. That would mean that MB is half of AB. So MB equals 1/2 of AB as well. Now we're actually going to prove that each part is half of the whole. We won't use that one a whole lot this year. We'll use it a few times. Segment subtraction theorem, we will use a few times. So it says basically, it's kind of an addendum to the segment addition postulate. This one comes directly from this, and you're actually going to prove it in your homework assignment upcoming, that if A dash B dash C, then instead of adding the two parts to get the whole, you can take the whole length AC and you can say that it's equal to, let me move this over here. I'm not going to write both of them. AM is half of AB and MB is half of AB. So you can take the whole segment AC and you can subtract a part of it and get the remaining part. You can also do AC minus BC equals AB. That is super easy to prove because you just take segment addition postulate and subtract something on each side. All right, the next one is the common segments theorem and the converse of the common segments theorem. These are theorems that a lot of geometry classes don't go over, but we will use them infrequently, occasionally. And if you don't remember them, don't worry, because like it's easy to get them confused. And so I will usually remind you of them if we're going to use them for something. So basically it says if A is between, or B is between A and C is between B and D, and AB is congruent to CD, then AC is congruent to BD. I'm going to draw a picture that's going to make this make sense, just like I did in class. So I'm going to draw a picture of that right here. Here we go. A, B, C, D. So AB is congruent to CD. That means that AC is congruent to BD. And what I normally do in class is I throw some numbers on here to make it make sense. It's always okay to throw some numbers on something to make it make sense. But when you prove it, you can't put numbers on it because you have to keep it general so it works regardless of the numbers. So let's say this is 2 and this is 4. Well, AC would be 6 then. And then it says here AB is congruent to CD. So let's make this 2. BD would also be 6 because you can tell they share a common segment BC in the middle that's getting added to both of the 2. So that hopefully will make sense. Now let's look at the converse of the common segments theorem, which is going to basically switch these two parts because we know a converse switches the hypothesis and conclusion. So again, if we have this between situation and the big overlapping parts are equal, then we can say that the small end parts are equal. That C did not turn out well. Let's fix that. Okay, so in other words, if we reverse it a little bit, take these off, and we say that AC is equal to BD, and let's say they're both, I don't know, I'll just make up something, 5.5. Then we can subtract 5.5 minus 4 to get the CD is 1.5. And we can take this 5.5 and subtract the 4 and get this as 1.5. This would be really easy to prove using the segment subtraction rule right here. So those two rules are converses of each other, and they're really easy to get mixed up. I just remember the common segments theorem starts with the little parts equal. Okay, I'm not going to highlight any of those because we don't use them a whole lot. Okay, we will use these a whole lot, all 3 of them. You already know what reflexive, symmetric, and transitive are because we had them as properties of equality. And I'm calling them properties here as well, but because most teachers, most books, most state and standardized tests treat them as properties. But the truth is they are actually theorems that can be proven. I'm actually going to have you prove one of them in your homework assignment. But they're pretty simple and easy to understand. So if you have a segment, it's automatically congruent to itself. So AB, the segment, or whatever you want to call it, is congruent to AB, the segment. And it seems really silly to say, well, why would we need to say that? Of course, every segment is congruent to itself. It will become very apparent when we do our triangle units because we might have 2 triangles next to each other that share that segment AB. So we have triangle 1 here on the right and triangle 2 on the left. And maybe we want to show the triangles are congruent using some stuff you don't know yet. But that would mean that AB in triangle 1, this segment, is congruent to AB in triangle 2. So it's congruent to itself. And it's important to realize that that's coming up. But we probably won't use that a whole lot right here. Symmetric and transitive, we are going to go ahead and use a lot. So if AB is congruent to CD, oh, I meant to put these as segments because we're saying congruent. They're segments, not lines. Lines are infinite. That implies that segment CD is congruent to segment AB. Okay. And then transitive, we know that if two things equal the same thing, they are equal to each other. So if AB is congruent to CD and CD is congruent to EF, then we can say AB is congruent to EF. So we will use that a lot too, because the easiest way to prove two things are equal is to show that they're both equal to a third different thing. You can also use transitive if they're equal to equal things, but we'll fold that in later. All right, some formulas which we don't use a whole lot in proofs, but I'm still going to briefly review them because they might sneak in a little bit. Midpoint on a number line, all these formulas we have done before in class. So we know midpoint on a number line is when you take the two endpoints and divide by 2. Midpoint on the coordinate plane, x1 plus x2 over 2, y1 plus y2 over 2. Distance on a number line, absolute value of a minus b. Distance on the coordinate plane, that formula that we've done before. We've already actually proven the distance formula on the coordinate plane. We might come back and prove it again a little bit more formally with Pythagorean theorem. And slope. We might use that later to say prove something is a parallelogram by showing the opposite sides are parallel and have the same slope. We'll come back to that later. Not yet, though. We're going to be doing more simple segment proofs right now. All right, let's talk about some background information on proofs, and then we will end this video and go on to do our next video where we actually write some proofs. So proving a theorem. When you prove a theorem, we write the theorem in conditional form. So like this first theorem we're going to prove in the next video is already written as an if-then conditional statement. We use the hypothesis to devise a set of given information. This first one's going to be pretty basic because this is the given information. Sometimes the hypothesis has the given information. Sometimes it's written in all words, no symbols, and so you make up your own figure and give it some names to fit that information. We use the conclusion to find what we're going to prove. Sometimes it's words and we have to name our own figure for those things. And you will get to see that coming up. Mark given information on the figure. Yes, you always do that to start with and draw your picture. Use the conclusion to divide. Oh, we already did that. Then starting with given information, use what you know to create an argument of statements, syllogisms and detachments. In other words, if this is true, then that is true. If this is true, then that is true. And by the time we get to the end, that means if this is true, the final step is true by a bunch of syllogism. To arrive at the statement you're trying to prove, each statement must be justified with a postulate, property, definition, or theorem that we have already learned. So yes, as we have our statements, we're going to justify them with something that we have already learned. And you can never, ever, ever use a theorem to prove itself. So if I'm writing a proof of the common segments theorem, I cannot use the common segments theorem to prove it. It's like writing a definition for a word. You can't put that word in the definition. So these are some things that you will keep in mind as you're writing proofs. Later, after we get a little practice under our belt and you start writing proofs on your own from scratch, we will talk about forwards and backwards thinking, but we don't need that right now. All right, so that is the end of this video on the reasons that we commonly use in segment proofs. I'm going to stop the video here and join us for the next one where we will actually do 3 example proofs together to make sure you're ready to start doing some fill in the blank proofs.